Welcome to this explainer. Today we are diving deep into the absolute fascinating physical properties of metals. And honestly, we're setting up a bit of a battle here. Because on one side, we have the rule makers. You know, those standard expectations we all have about what a metal is supposed to be. But on the other side, we've got the chemical rebels. These are the elements that look at the strict rules of physics and chemistry and just decide to do their own completely unique thing.
So let me ask you something. When you think of a metal, what does it look and feel like in your mind? If you're like most of us, you're probably picturing something heavy, right? Something rock hard, perfectly shiny, and maybe making a loud, obnoxious clanging sound if you happen to drop it on the floor. But what if I told you there are actually some metals out there that are so shockingly soft you could literally cut them in half with a standard butter knife right out of your kitchen? It's crazy, but it totally challenges everything we assume about the materials that literally build our modern world.
And that dynamic is exactly what we're dissecting today. We're going to look at a complete map of the 10 physical properties of metals. Now, I know, looking at this all at once, it seems like a massive amount of information right out of the gate. But don't worry, we are going to break it down step by step. What I really want you to notice here is the pattern. For almost every single standard rule listed on this map, right below it, there's an exception. There is a rebel element just completely defying the standard. So by the end of this explainer, you are going to see exactly how the periodic table loves to keep us on our toes.
Let's start with Section 1, Sights and Sounds, Visual and Auditory Traits.
Okay, so the crucial rule when it comes to color is that the vast majority of metals usually have this standard silvery or silvery gray color. Just think of everyday things like aluminum foil, steel beams, or silver coins. That's the baseline rule. But we almost immediately run into two of our most famous rebels. Gold absolutely refuses to be gray, showing off that brilliant, highly sought-after yellow color instead, and then copper stands right alongside it with a very distinct, warm, reddish-brown hue. Honestly, these two visual rule breakers have driven human economy and art for thousands of years, specifically because they just don't look like the rest of the pack.
Now, what about luster? Metals are famously lustrous, which really just means they have a highly shiny, reflective surface when you polish them up. We fully expect metals to gleam, but not all of them actually do. Sodium, which is represented by the symbol Na, and lead, represented by Pb, break this shiny rule completely. They are decidedly non-lustrous. Instead of a brilliant, reflective shine, they present this much duller, flatter appearance that definitely betrays our standard expectations of what a metal should look like.
Moving from the eyes to the ears, we encounter a great word, sonorous. The rule here is that metals are sonorous, meaning they produce a deep, reverberating, ringing sound when hit. I want you to just imagine striking a large bronze bell or hitting a steel tuning fork. That lingering, resonant auditory experience, that is the very definition of being sonorous, and it's a classic hallmark of metallic structure.
But once again, we have our conspirators. Just look at this lineup of non-sonorous rebels. If you were to strike mercury, sodium, potassium, or lead, you are absolutely not going to get a beautiful ringing bell tone. You're going to get a very dull, very disappointing thud. They completely lack the structural rigidity required to carry those sound waves in the way that standard metals do.
Moving on to Section 2, Toughness and Weight, Physical State and Density. So here is perhaps the most famous rule of all. Most metals are solids at room temperature. Obviously, right? It's foundational to how we build bridges, cars, and massive buildings. But there is one solitary, absolutely fascinating rebel that throws this entire concept right out the window. Mercury, symbol Hg, exists entirely in a liquid state at room temperature. It flows, it beads up, it splashes, all while still being a dense, true metal. It's just an incredible visual anomaly.
And building right on that, metals are supposed to be hard and have a high density. They are heavy and they are tough. But remember earlier when I asked if you could cut a metal with a butter knife? Well, here is your answer. Sodium, Na, and potassium, K, are massive exceptions to the hardness and density rule. They have incredibly low densities, and they are so surprisingly soft that they can be easily sliced right through with a standard kitchen knife. It is literally almost like cutting into cold butter or a block of cheese. It's wild to think of a pure metal behaving this way.
Let's look at Section 3, Shape-Shifting and Power, Ductility and Conductivity.
Two of the absolutely most vital properties of standard metals are their ductility and their malleability. Ductile simply means the metal can be stretched and drawn out into very thin wires without snapping. Malleable means it can be beaten or rolled into incredibly thin sheets without shattering into pieces. Elements like silver, copper, and aluminum are absolute superstars at both of these. This shape-shifting ability is quite literally the foundation of all our modern wiring and packaging. But when we talk about ductility specifically, I really want to give you a sense of scale here. Gold is the most ductile metal on the entire periodic table. To understand just how ductile it is, if you take merely a single gram of gold, we're talking a tiny bead roughly the size of a grain of rice, you can draw that out into a thin wire that stretches for 2 kilometers long. That is over a mile of continuous wire from one tiny gram. The structural integrity going on there is simply staggering.
Next up, let's talk power transfer. Metals are, as a general rule, fantastic conductors of both heat and electricity. Silver actually takes the crown as the absolute best conductor of both. Copper and aluminum are close runners-up, which is exactly why we see them used so much in our power grids and cooking pots. Gold and tungsten are also fantastic electrical conductors. This is the standard, reliable behavior that allows our electronics and electrical systems to function worldwide.
Yet, even here, we manage to find rebels. While metals are supposed to be great conductors of heat, lead and our liquid friend mercury are actually quite terrible at it. They act as poor conductors, actively resisting the flow of thermal energy in a way that completely sets them apart from the copper and aluminum champions we just looked at.
On to Section 4, the heat test, melting points.
The general rule of thumb is that metals have immensely high melting and boiling points. You generally need massive, industrial-grade furnaces to turn solid metal into liquid. But, as you might have guessed by now, our frequent rebels, sodium and potassium, pop up once again. They completely defy expectations with remarkably low melting and boiling points compared to their peers.
But to really truly drive this exception home, we have to look at gallium and cesium. The melting point of gallium is just 30 degrees Celsius, and cesium is even lower at 28 degrees Celsius. So what does that mean practically for us? It means if you hold a solid piece of gallium or cesium in your bare hand, your normal, everyday body heat is actually enough to break down its metallic structure. It will literally melt into a silvery liquid puddle right in the palm of your hand. It's a completely surreal, visceral experience that proves just how widely varied these elements can be. Finally, Section 5, the ultimate rule breakers, summarizing exceptions.
I want you to walk through this fantastic visual cheat sheet with me for a second, just to lock all this in your memory. Look at the patterns here. If you need a liquid metal, it's mercury. If you're looking for incredibly soft metals with low densities, your absolute culprits are sodium and potassium. Looking for a pop of color? Gold and copper break that silvery rule. If you want dull, non-lustrous elements, you look to sodium and lead. And if you happen to drop them, remember that mercury, sodium, potassium, and lead are our non-sonorous rebels, giving you a dull thud instead of a nice ring. Honestly, looking at this, sodium really is the ultimate repeat offender here.
Let's revisit our anchor map one last time. When we started, this might have looked like a chaotic wall of text and chemical symbols. But look at how much complex information you've just mastered through this structured breakdown. You now know not just the 10 defining physical rules of the metallic world, but precisely which rebellious elements subvert those rules at every single turn.
But as we wrap up this explainer today, I want to leave you with a bit of a provocative thought. We've just spent all this time establishing what a metal physically is, only to repeatedly prove that elements like sodium, mercury, and lead break almost every single one of those physical rules. So, if so many elements break the physical rules of being a metal, what really defines one in the first place? Well, to answer that, you have to look past the physical and dive deep into the invisible, subatomic world of their chemical properties. But that is a whole other exploration for another time. Thanks for learning with me today.